Welcome to Chapter 11 of MEC410, Design of Machine Elements. This week we're going to study keys, couplings, and seals, which are elements that connect shafts to gears and other rotary elements. We have some homework problems from the text for you, which is shown here with some special notes. Please make sure to follow them. We've also got some additional homework problems for you to solve, mostly because the textbook didn't have homework problems on these subjects, and it's always good to have a little practice. In Chapters 7, 8, 9, and 10, we discussed how to specify pulleys, sprockets, and gears. And in Chapter 11, we're going to discuss how keys and couplings attach these rotary elements to shafts and how seals seal the lubricating fluids in transmissions. Keys are placed between a shaft and the hub of a power transmitting element. The key forces the shaft and the hub to rotate in sync. So these are some components from a machine tool. Here's our what essentially acts as a shaft. This part I'm pointing to acts as the hub. And the key is this rectangular shaped part that allows the torque of the hub to be transmitted to the shaft. Or it allows the torque on the shaft to be transmitted to the hub. Now the hub could be the central part of a gear, chain, or sprocket. And most common keys have square and rectangular cross sections. These are known as parallel keys. The one in this figure has a rectangular cross section. And then the key seat is a notch which must be machined in both the hub and the shaft to fit the key. So here you have this little U-shaped cutout in the shaft. That's the notch in the shaft. And up here you have a U-shaped cutout in the hub, and that would be the notch in the hub. Key sizes are specified per the shaft diameter using Table 11-1. First, you specify your shaft diameter. You find out where it fits in these two columns. This is a over-under chart, if you will. It says that if your shaft is in between this number on the left column and this number on the second from the left column, that's the row you're on. So for example, 1.260 inches, you'd be on this row. And then you get the width of the key, and you would get the height of the key. And this chart is for rectangular keys. Parallel keyseat depths are symmetric for both the shaft and the hub. And the length of the key should be a substantial portion of the hub length, and we're going to show you how to calculate that. To use these diagrams, if you were to make a drawing of a hub or a shaft, you have to be careful what the formula is referring to. In this case, the formula for y is the distance from this little point here where the arc ends to the center line of the key, so very small number. Or you could have S specified, and that's the distance from the bottom of the key seat to the bottom of the shaft. Or in the depth of a hub key seat, you could have T specified, and that is the distance from the top of the hub to the bottom of this central arc here. Here on the lower right side, we define the various dimensions that are in the diagrams. When you assemble a key to a hub and shaft, first you do step 1, which you place the shaft, here's our shaft, into your machine. So you would put it into this collar. Step 2, you would place the key, here's a key, here's another rectangular key, on the shaft. Step 3, you would slide the hub, in this case the hub of the sprocket. So there's a sprocket, and then this middle section here is the hub of the sprocket. Place it over the shaft. And step 4, if there's other hubs that have to be placed on the shaft, you would put them over. It looks like in this example we've already got 2 sprockets and 2 hubs on the shaft. It looks like we've got room for 1, 2, I'd say 4 more. And note that the keys do not stop the axial motion of the hubs. So the hubs are still free to move in this axial direction. All they do is make sure that the torque of the shaft is transmitted to the hub, which in this case is sprocket. There's other geometries of keys, more complex ones shown in this diagram. You have taper keys in the upper left, which allow the keys to be pulled out of an assembly from the same direction they were installed. That's kind of convenient. You have a pin key, which is basically just a little cylindrical pin, which goes in a arced shape hole. And they're nice and cheap and they're easy, but they're only for work for the smallest of radial loads because they shear easily. And then you have Woodruff keys, which is a cross between a circular key and a square key. In other words, the cross section is this square, but in the plan view you have an arc, and the idea is that the key gets wider and wider in the middle and then narrower on the ends. And they make a good compromise between cost, assembly, and load, and in fact they're the most common ones because they are the easiest to assemble in a machine. And we have a nice picture here showing how that's done. Here's the Woodruff key, so there's your arc on the bottom and your flat on the top. And there's your Keyseat, which has an arc in it in one dimension and square cross section across the other dimension. And the nice thing about the Woodruff keys is that once this person places the key in that hole, it'll basically move to center itself. Now you can either do it with your finger or you can take a wrench and install it. But this idea that it's self-centering is what makes it so easy to fit a Woodruff key into the semicircular keyway in the shaft. And then of course on the hub, because the top of the Woodruff key is flat, the hub then has a key seat that's just a machined rectangular cutout, as opposed to the shaft, which has the arc cutout for the bottom arc surface of the Woodruff key. Keys, shafts, and hubs can be damaged if stresses exceed yield limits, and here's an example of the use of a square key in a key seat that wanted to have some rounding on this edge, and that created a lot of stress and eventually the entire shaft cracked. In this slide we will calculate the minimum key length for a rectangular key to avoid failure due to shear stress across the shaft-hub interface. On the right side we have a diagram of our system. There's the shaft. It's rotating in the clockwise direction, transmitting torque to the hub. Here's our rectangular key seat. And because of the transmission of torque through this rectangular element, we wind up getting a shear force and a shear stress on what's called the shear plane, which is the plane in the center. And the area of this shear plane is W, the width of the key, times L, which is the length into the page of the key. And the force is equal to the torque divided by the diameter of the shaft over 2, which is basically torque over the radius of the shaft. And then the shearing stress is the force divided by the shear area, A sub s, and that's equal to the torque over d over 2 times WL, which is 2t over dWL. We can set the shearing stress equal to a design stress in shear for the maximum shear stress theory, in which the design stress, tau sub d, equals 0.5 times SY, the yield strength, divided by N, which is the safety factor. And then the required length of the key by letting tau equal tau d and solving for L is that the minimum key length L is 2 times the torque T divided by the design stress times the diameter of the shaft times W, the width of the key. You use this formula to calculate for the key length if the key material is the strongest and a rectangular key is used. In other words, the key material in this formula is stronger than the shaft or the hub material. We can also calculate a minimum key length in a rectangular key to avoid failure due to compression on the side of the key or the key seat. We have the same plan view of our shaft and hub, but taking a look at the key itself, we see that the force in compression is distributed over a bearing area L the length times half the height. You have a compressive force acting on the top half of the key when it's in the hub, and you have a compressive force acting on the bottom half of the key that's in the shaft. That's why you're using a compressive area A sub C equal to L times the height divided by 2. We can define a design stress for compression as sigma D equals S sub Y, the yield strength, divided by N, the safety factor. And then the compressive stress is equal to sigma equals F divided by A sub C, which works out to 4 times the torque divided by the diameter of the shaft times the length of the key times the height of the key. And if we let sigma equal to sigma sub d, we get that the minimum key length for compressive loads is 4 times the torque divided by the design stress times the diameter of the shaft times the height of the key. And we calculate this for the hub and the shaft if the key material is the strongest, or if a rectangular key is used. We can also calculate a minimum key length to avoid failure with a rectangular key due to compression on the side of the key, or the side of the key seat. Our diagram is the same as before, but now we're concerned with the stress in the key. And this assumes that the key is the weakest material, which is the most common occurrence. So for the design of a square key in which the strength of the key is lower than that of the shaft, we combine equations 11.2 and 11.4, and we produce the same result either way. Substituting the design stress into either equation gives us the formula L equals 4 times the torque times the safety factor N divided by the diameter of the shaft times the width of the key times the yield strength. You evaluate the length from equation 11.4 if either the shaft or the hub has a lower yield strength than the key, but if the key is the weakest material, and this is most common, use equation 11.5 as shown. Use a table 11-4 for key material properties. The most common key material is the weakest one, carbon steel 1018. It has a tensile strength of 64 KSI and a yield strength of 54 KSI. And here's an example of a key problem, number 11-1 in our book. For problems 1 to 4 and 7, determine the required key geometry, length, width, and height using SAE 1018 steel for the key. Specify a key for a gear to be mounted on a shaft with a 2-inch diameter. The gear transmits 21,000 pound-inches of torque and has a hub length of 4 inches. Here's our key. There is our shaft. There's our gear. And in this case, it's showing the key going all the way through and out the other side. The hub length is the distance from here, where my mouse is, to there, which is 4 inches. So now we're going to calculate, does the key need to do what's in this picture, longer than 4 inches, or is some number less than 4 inches acceptable? We use a table 11-1 for a 2-inch shaft, which is between 1.75 and 2.25, and we find that the key is indeed square, a 1/2 inch width and a 1/2 inch height. Here in the gray shaded area, we put all of the input data as defined in the problem. Being SAE 1018 material, the key has a yield strength of 54,000 psi, and we've chosen to have a design factor N of 2. The minimum key length is then calculated as 4Tn divided by D times W times Sy, and it turns out to be 3.111 inches, which is a little less than the 4 inches of the hub. So in this picture, if you really went for the 3.11, you actually wouldn't see the key because that's less than this 4-inch distance here of the hub width. The key would be internal. Usually in key problems, people tend to round up. So if they get a number 3.11, they tend to round up to the nearest commercially available length that's sold. In these slides, we will discuss how you calculate key lengths and minimum acceptable torques for Woodruff keys. And in this slide, we find the shearing plane surface area, A sub s, for a Woodruff key. Here's our diagram on the top from before. Slightly different shape to the Woodruff key depending on whether the shaft diameter B is less than 1.5 inches or above. When the shaft gets over 1.5 inches, they tend to put a little flat here on the edges, as opposed to for the small ones where they machine it all the way to a point. The shear stress is still tau equals force divided by the shear area, and it's a rather complex formula that we have to follow. B is the nominal diameter of the cylinder of which the key is a part, which normally means the shaft diameter. W is this width of the key in this dimension. C is the full height of the key, meaning what you see in this right side view or from the top surface to the bottom of this shaft diameter. And D sub s is the depth of the key seat in the shaft. From this point where my mouse is to the bottom, the key would be sitting in the shaft and would be handling the load from the shaft. And this area that I'm going to draw for you, you see where my mouse is, that area is where the key hits the hub. So the shear area is equal to 2 times the width times the square root of D sub s times capital B minus D sub s. And we can find the maximum torque transmitted using a Woodruff key due to the shear stress. And here what I'm showing you is sort of an odd picture. It's the Woodruff key now, but in the plan view, which is this view, we're looking from the left side of the key. You really do see a rectangle. And you have shear acting on the side of the Woodruff key, which is what we're trying to show. Part of the Woodruff key is buried in the shaft, part of it's buried in the hub. And the force is the torque divided by the diameter over 2. The shear stress is F, the force, divided by A sub s, the shear area. Similar to with rectangular keys, we have a design shear stress tau d, which is equal to 0.5 times the yield strength S sub y divided by n, the safety factor. And we let tau equal tau d and substitute t divided by d over 2 for F. And then we find that the maximum torque, which is limited by shear stress, that can be transmitted by a Woodruff key is T equal A sub s times Sy times the diameter of the shaft over 4 times the safety factor. In order to find the maximum torque transmitted by a Woodruff key with regards to compressive forces, we need to find A sub c, the compressive bearing surface area for a Woodruff key. And the equations to do this are even more complex than what we had in the prior slide. The compressive stress sigma equals the force divided by A sub c. And you have to be careful in this nomenclature that there is, in these formulas down at the bottom, a dimension F, which is the total width of the Woodruff key as it sits in the shaft. So F that I'm showing you here does not mean force F. We have these 3 constants G, L, and J that you calculate per formula. The bearing area in the shaft AC is a different number than the bearing area in the hub, because the bearing area in the shaft is here. That's what I'm showing you with my mouse. And we have the bearing area in the hub is up here. And you don't get the same number. And that's why these 2 formulas here, using these complex constants that we have to calculate, are not the same. Once we have those calculations, we can find the maximum torque transmitted using a Woodruff key due to compression. It's just that we'll have a different amount of torque depending on whether the area we're talking about is the area in the shaft or the area in the hub. The compressive stress is sigma equals the force F divided by the area A sub C. And we define a design stress for compression, sigma d equals Sy over n. We then let sigma equals sigma d, and we substitute T over d over 2 for our force F. Then the maximum torque, which is limited by compressive stress, that can be transmitted by a Woodruff key is torque T equals A sub C times S sub Y times the diameter of the shaft over 2 times the safety factor. Table 11-3 shows Woodruff key dimensions. They give us the key number and they give you all the critical constants that you need. The nominal key size, W times B, F, C, the shaft keyseat depth we've been calling D sub S, and the hub keyseat depth. In key problem 11-13, we're going to compute the torque that could be transmitted by the key of problem 10 on the basis of shear and bearing if the key is made from SAE 1018 cold-drawn steel with a design factor of n equals 3. And then we're going to show you a drawing of what the Woodruff key connection looks like. The shaft has a diameter of 1.5 inches, and we will use a 1210 Woodruff key. Here is our input to key problem 11-13. We use a table -3 to get the Woodruff key dimensions for a key number 1210. W equals 3/8, B equals 1 1/4, F is 1.24, the height of the key C is 0.544, D sub S, the shaft key seat depth is 0.3545, the hub key seat depth is C minus D sub S, which is 0.1935. We dial all those numbers into this gray shaded area. We've chosen a design factor of 3 and a yield strength of the key of 54,000 psi, which corresponds to SAE 1018 material. Here's our area calculations for key problem 11-13. First we solve for the shear plane surface area A sub S, then for bending area constants G, L, and J. Then we can calculate, once we have all our constants, the bending area in the shaft and the bending area in the hub. Now we're going to calculate the maximum torque 3 different ways. For the torque in shear stress, it depends on A sub S, the shear area, we get 674 inch-pounds. And for the max torque due to compressive stress along the shaft, we get 476 inch-pounds, because that uses the compressive area that's in the shaft. When we calculate the max torque per the compressive stress along the hub, we get a different number. We get a much bigger number, 1159 inch-pounds, because AC of the hub is a bigger number than AC of the shaft, therefore it can handle more torque. So when you have 3 numbers like this, you have to take the minimum of the 3 numbers to figure out what's the maximum torque that the shaft can handle. So in this case, it's only 476 inch-pounds, because if you go more than that, you're going to fail due to compressive stress in the area along the shaft. Splines are a very different way of connecting rotating shafts. They're machined into a shaft, and mating grooves are machined into a hub. So here's the splines that are in a shaft. They're raised elements. And then the negative of those elements are called grooves. And then this shaft with the splines on them gets fit inside the hub with the grooves. And then the shaft transmits the torque to the hub. They're used to transmit torque in automotive drive shafts, and they provide highly uniform transfer of torque because 4 or more and usually 6 or more splines are always used. The surfaces of the splines and grooves are hardened to resist wear, so that's this outer surface on the shaft and these surfaces on the hub. Splines allow for small axial motion between the shaft and hub. Axial is in the long direction on the shaft because there's nothing stopping the shaft, what's in the hub, from moving in and out of the hub. It's not able to rotate other than a couple of thousandths of an inch. That's what allows it to transmit the torque, but it can still transmit in the axial direction a small amount in case the shafts and the hub need a little clearance. The end view of a straight-sided spline is shown here in this diagram. Capital D is the major diameter. Little d is the distance from the center to the top of the tooth. That's the minor diameter. W is the width of the spline, and H is the spline depth. These numbers are roughly analogous to screw threads. H and small d vary by the mating conditions between the shaft and the hub. That's per this table 11-5. The number of splines in this table is either 4, 6, 10, or 16. The table shows all the dimensions, capital W, small h, small d, as a function of the large diameter d. And there's 3 types of fits, A, B, and C. Use fit A, the permanent fit, when the shaft and the hub are not to be moved after installation, meaning it's going to be a very, very tight fit. B fit is used if the hub will be moved along the shaft without a torque load, meaning you take the shaft and you manually move it in this direction when the machine is not moving. And C is if you want the shaft to be able to move axially when you're transmitting torque. So here the spline on the shaft is in the hub, and you're not only moving torque, but you want the shaft to move in and out. C is the loosest fit. The torque capacity for splines per table 11-5 is based on the limit of 1,000 psi bearing stress on the sides of the splines. So here's the sides of the splines, from which the following formula is derived. The torque is 1,000 times capital N times R times H. N is the number of slides. This picture has 6. R is the mean radius. That's from the center to this midpoint here. And H is the depth of the spline, distance from the inner diameter, small d, to the outer diameter, large d. And the torque capacity is per inch of length of spline. But we also have these equations here for R and H, and if you do the algebraic substitutions, you find that the torque is then equal to 1,000 N times large D squared minus small d squared over 8, and that comes from substituting capital R and the values for capital H into this equation, T equals 1,000 NRH. If you do some further math, you find that small d in all of these splines for a certain number of splines in fit is designed to be a ratio of large d in all cases. A different ratio depending on how many splines and what the fit is, but always a ratio. Here we're showing one example where it's a B fit and N equals 6. Small d is 0.850 times large d by definition of the shape. And then you can get rid of small d in this equation and you find that the torque is 208 times d squared, or d equals the square root of t divided by 208. And it makes for a very simple table. It tells you that based on the large diameter of the spline, you always have a torque capacity that is equal to a fixed constant, different numbers, 139, 219, 143, etc., etc. We give this fixed constant the letter capital K times the diameter squared. So all you really need to know is the straight spline, what's the large diameter, or what's the number of splines in the fit, and then you can always figure out the torque capacity. Here's a simple example straight spline problem 11-5. They wanted to specify a suitable spline having a B-fit for each of the applications in problems 1-4. We've decided to design a spline solely for problem 11-2. So instead of specifying a key for a gear carrying a 21,000 pound-per-inch of torque mounted to a 3.6-inch diameter shaft with a hub length of 4 inches, we're going to design a spline. So I X'd out key and I put it in. This little key here doesn't exist anymore. I put in a little side view picture of a spline. That's what we're designing. We know the shaft diameter D is 3.6 inches. The torque on the gear T is 21,000 inch-pounds and the length is 4. The required value K is 405 because K equals T divided by D squared L. But there aren't any constants on this table 11-6 that are 405. We have a 344 and a 521. So you always pick the larger torque capacity because you want to make sure the spline's going to work. And then that says K equals 521. Select a B fit. And it's 16 splines, and that's our solution to the problem. Involute splines have teeth and grooves that are similar to spur gears, and this geometry makes them better at self-centering. So here is the teeth of the spline, and then the matching pattern. And these teeth of the spline kind of look like spur gears. The major diameter is to the top, minor diameter to the bottom. Circular pitch small p is defined similar to a gear tooth from one point on a tooth along the pitch diameter to the corresponding point on the next tooth. And the pitch diameter is this center line position within the tooth relative to the middle of the spline. You also have N equals the number of spline teeth, capital P equals the diametral pitch, capital D is equal to N / capital P, that's the pitch diameter, and small p, which is pi divided by large P, is the circular pitch. For the minor diameter, the internal minor diameter is here, and that's equal to N minus 1 over P, and the external diameter is this one here that I'm pointing to, and that equals to N minus 1.35 over P. Major diameters have their equation shown here on the bottom right. The sizes and dimensions on involute splines are also similar to the gear teeth. The diametral pitch then is the number of teeth per inch of pitch diameter. Diametral pitches come only in even numbers, usually from 6 to 60, but sometimes up to 100 teeth on 45-degree splines. This chart shows the formal definition of circular pitch, which is very close to the definition of circular pitch on a spur gear. In particular, though, look at the tooth thickness definition T. That's the thickness of the tooth as measured along the pitch circle. So from this point all the way across to that point is what we call the tooth thickness. The tooth thickness is just the circular pitch divided by 2. The torque capacity for straight and involute splines is shown per figure 11-7. The major spline diameter D is shown on the y-axis. The x-axis shows the torque capacity per inch of spline length in pound-inches per inch. The x-axis is logarithmic. And for the involute spline, you must calculate the major diameter using the formula in figure 11-8, which are these. Here's an example of how to determine the torque capacity of an involute spline. The question says, what's the torque capacity of major diameter fit involute splines with capital P, the diametral pitch equal to 8, number of involute spline teeth N equal to 16. Per figure 11-8, we calculate major diameter D as N plus 1 over P, which is 2.13 inches. Then we go to the y-axis of this chart, find approximately 2.13 inches, read across, find out where it hits this line for involute spline Read down and we see that the torque capacity per inch of spline length is roughly 12,000 inch-pounds per inch. Pinning is a low-cost but low-reliability means of connecting a shaft and a hub. In order to put a roll pin, such as the one shown up here in the upper right, into a pair of shafts, you drill a hole of diameter small d through and out the other side of both the shaft and the hub, shown by the section view over here. The problem with doing this is that these roll pins are rather fragile and they don't really support a whole lot of torque, which is why the most common application for pinning is to have the pin act as a shear pin. In other words, it's a mechanical fuse to uncouple the shaft of diameter d and the hub of diameter d1 in the event that too much torque is applied to the shaft. We can calculate that torque from the equation T equals 2F times D over 2, which is equal to F times capital D, and with the symbol small d representing the pin diameter, the shear stress in the pin is tau equals F divided by A sub S, where A sub S is the shear area, pi times small d squared over 4. And so the shear is equal to 4 times the torque divided by capital D times pi small d squared. Then we can calculate the required diameter for a pin to shear at design shear stress tau d is equal to the square root of 4 times the torque divided by large diameter d times pi times tau sub d. A split taper bushing is used to connect a shaft to a pulley, or to a sheave as it's sometimes called. It's shown here in the lower left corner of the slide. In a split taper bushing, there is a seam on the side of the bushing so that when you assemble the bushing into the pulley, the seam will collapse and will hold it in tight. There's a slot in the bushing for a key to attach the shaft. Taper part of the bushing gets its name from the fact that the diameter is smallest at the top, such that when you assemble the bushing into the pulley, the small part goes in first, and the farther you push the bushing into the pulley, the larger the diameter of the bushing that contacts the pulley. You will then get a press fit of the bushing in the pulley. The seam in the tapered bushing will close, and by the time you fully insert the bushing in the pulley, this seam will be totally closed and the bushing will be in there very tight. You then attach the screws of the bushing to the pulley. Then you insert the shaft into the tapered bushing using the key. Rigid and flex couplings are used to align a pair of shafts. A rigid coupling assumes a near perfect alignment of two shafts, so one shaft goes in from the right, the other shaft comes in from the left. You then tighten the bolts, and it won't work if the axes of the shaft are not virtually collinear. The flex couplings allow for some axial misalignment of the axes of the shaft because these little slots in the flex couplings can give, and the whole flex coupling can become a little miniature slinky taking on an angle. But then the shafts must move slightly to accommodate the motion within the coupling. A rigid coupling torque transmission is limited by the max shear stress allowed in the bolt. And in a rigid coupling, we arrange an even number of bolts in a bolt circle, diameter d sub bc, bc is for bolt circle, and the shear force on the bolt circle is equal to the torque applied to the shaft divided by the bolt circle diameter divided by 2, which is just 2 times the torque over the bolt circle. And if n is the number of bolts, the shear stress in each bolt is tau, where tau is the force divided by the shear area A sub s, which is F divided by n, the number of bolts, times the shear area per bolt, pi d squared over 4. which is then twice the torque over the bolt circle diameter times n times pi small d squared over 4. And more importantly, we calculate for small d in this equation, and we find that small d is the square root of 8 times the torque divided by the bolt circle times n times pi times shear stress tau sub d, where the shear stress is the design shear stress in the bolt. And based on this equation, we know that if we have a certain amount of torque we want to transmit and a certain number of bolts in the bolt circle, we need to make the bolts a certain diameter, small d, in order to make that happen. Universal joints are used to transmit torque when angular misalignment between the shafts is greater than 3 degrees, a point at which flex couplings won't work. And they allow misalignment up to 45 degrees at low speeds for single universal joints. Double universal joints work with parallel shafts offset by large amounts. The video link shown here at the bottom gives you a very good depiction of how universal joints work. Shoulders and spacers are positioned on a shaft between mechanical parts. They separate two parts by an exact amount. So here is your spacer shown in the hatch. There's your gear, there's your bearing. The spacer makes sure the gearing is a defined amount of distance away from the bearing. Here's another spacer on the side. Another way you can create a fixed location axially of gears is you put a step change in the diameter of a shaft. The step change is known as a shoulder, and it acts as a hard stop in one direction for a mechanical element. So here's your small gear, there's your large diameter gear. This large diameter gear cannot move to the right because of this existence of the shoulder in the shaft, and the small diameter gear cannot move to the left because of the existence of the other side of the shoulder. Rings snap onto a groove in a shaft and also space components apart. Shown on the left are 4 geometries of a ring. The basic idea is that a ring is a thin metal part machined to standard dimensions. It holds mechanical elements in a fixed axial position, such as shown here in this picture. You have a groove, such as the one I'm pointing to. Then you take the ring, in this case style A, and you snap it into the groove. And at that point, whatever part is up against the groove is in a known location. Different types of grooves give different amounts of axial load that they can handle before the ring itself gives way. The strongest of all is this one called an external E-ring style, choice B. Lock nuts and lock washers are commonly used to retain bearings in place. This is an exploded view of a Timken spherical roller bearing pillow block, showing a tapered bore spherical roller bearing, adapter sleeves, other parts, and in particular lock nuts and lock washers holding the spherical roller bearing in place. So the roller bearing goes in this pillow. The tapered ring and the seal ring come in from one side. The steel stabilizing ring comes from the other side. Then this lock washer and the lock nut attach to hold the steel stabilizing ring, then the rest of the assembly in place. Seals retain lubricants in hydraulic actuators and valves and keep contamination out. So when you have a hydraulic cylinder where the piston is moving in and out of a cylinder that has oil in it, you have to make sure when the cylinder moves in and out that the oil doesn't leak. So these seals, known as U-cup seals, here's a nice picture of one in blue, and in the diagram they're shown in black, are used to keep the oil in place even when the seal itself is in motion because it's attached to the piston. You can watch this video on the bottom. We'll show you how those U-cup seals work. Vehicular universal joints connect the transmission to the rear drive wheels in trucks, and constant velocity joints connect the transmission to the front drive wheels. This video here that we have at the bottom gives you an excellent view of how universal joints are installed in automotives.